This video segment is part of a set of videos on basics in which we'll touch on just the bare essentials of laser measurements you might need to do and the tools that'll help you do them. In this short video, we'll review the ABCs of measuring laser beam power and energy. So you'll have a clear basic understanding of what the different sensor types are and when you would use which type. Our discussion will stay on a general level. Separate video segments will cover each particular sensor type in more detail. For specific help with the solution for your application, please speak to your Ophir representative or make use of the many resources available on our website, such as the Sensor Finder and the range of tutorials and training videos. In general, a laser measuring instrument consists of a sensor and a meter. The sensor is the front end, which receives the laser beam and generates some sort of electrical signal that represents it. The meter processes and outputs the result, for example, as a numeric display that a human user can read. The choice of sensor is physical. It depends on the physical characteristics of the laser beam, while the choice of meter basically depends on what functions you need performed with the results of your measurement. In this video, we'll have a general look at the various types of sensors, so you'll know where to start. Energy is the capacity to get a certain fixed quantity of work done. For example, 1 joule is what it takes to heat up about 1/4 of a gram of water by 1 degree Celsius. Power, on the other hand, is a rate of flow of energy. For example, 1 watt is 1 joule per second. We can talk about measuring the energy of a single pulse or of every pulse in a repetitively pulsed beam. We can measure power of CW beams as well as of repetitively pulsed beams. Determining which sensor is the right one depends on the type of measurement we need to do and its details. For measuring pulse energies, we use energy sensors. These are normally based on pyroelectric detectors, though for the very lowest energies down to picojoules, there are sensors that are based on semiconductor detectors. For measuring very low powers, from picowatts up to several hundred milliwatts, we normally use photodiode sensors. These are based on semiconductor detector elements, where light is converted directly to electrical current, which is then measured. Ophir offers several types for different spectral regions and power levels. For extremely low powers, down to femtowatts, we have a line of radiometers called the RM9 family. These have a chopper integrated with a sensor and make use of a digitally synthesized lock-in amplifier to ignore any signal that's not at the chopper frequency, and thereby reduce external noise by several orders of magnitude. That's what makes it possible to measure powers down in the femtowatt range, depending on the specifics. For powers ranging from milliwatts and up to tens of kilowatts, we normally use thermal sensors. These sensors absorb the light and first convert it to heat. The heat flows through the sensor and is in turn converted to an electrical signal, which is then measured. Thermal sensors are also useful for measuring energy of a single shot pulse, such as is sometimes used in certain industrial or medical applications. Ophir also has a family of thermal sensors that can measure position and size of a beam at the same time as measuring its power. These power, position, size sensors have the family name BeamTrack. For measuring divergent beams, there are 3 approaches. First is the integrating sphere, which is designed to capture all the light that enters it. Next is to simply use a sensor with a very large aperture and place it close enough to the light source to capture all of the power. Finally, you can capture only part of the beam, and then instead of total power or total energy, you'll be measuring power or energy density. Each of these involves some technical considerations, but that's for other videos. The specific choice of sensor model depends on a number of parameters, including the order of magnitude of power or energy. For example, a power sensor that can measure picowatts will probably be vaporized into plasma by a multi-kilowatt beam, while a sensor able to measure multi-kilowatt beams will not likely respond at all to a few picowatts. Spectral region. Different materials absorb light of different wavelengths to varying degrees. And beam diameter. No need to panic. Ophir offers a tool called the Sensor Finder, which does most of the thinking for you and offers you the correct solutions for your laser. You can find it on our website. There's also an advanced sensor finder if you're working with a diverging beam. We hope that this short video will help put things in order for you, so you'll know how to begin and what questions to start with. In separate video segments, we'll look a bit more specifically at each of the sensor types. Contact us to see how we can help you with your application, directly, through our local representatives, or via our website.